Hello. In this video we are going to talk a bit about the switch operation. We're going to talk about the network traffic domains, we are going to talk about bridges and switches, we are going to talk about traffic types in Ethernet, flooding and learning of traffic and the addresses, and we're going to talk about the switching memory tables. In other words, we're going to talk about how switches store the information they learn about the addresses in the network. When we are talking about network traffic domains, we are really talking about the collision domain and the broadcast domain. Let me explain that a little bit. The picture that you can see here behind me is the original drawing for the Ethernet network. This is what all modern networks are really designed around. This is the drawing that was made sometime in the past in the Xerox Palo Alto Research Center, and it shows how different stations can connect to a thick yellow cable that interconnects all of them. In other words, it shows us how the Ethernet was originally designed and envisioned as a bus type architecture. Let me explain that just a little bit. What I mean by a bus style architecture is that the original idea behind the Ethernet was that multiple stations, let's call them A, B, and C, would connect to the network. That would be really just one cable, and that they would all three connect to that cable. That meant when station A was transmitting the traffic to the cable, this traffic would eventually reach both B and C. But it also meant when, for example, B was transmitting, this traffic would reach C, but it would also reach A. This created a kind of a problem. The problem called the collisions. If station A tried to transmit the traffic at the same time when station B attempted to transmit the traffic, those frames, that traffic, would collide on the shared cable, on the shared bus. And we cannot have that. This needs to be either detected or avoided altogether. In Ethernet, that implements a technology called carrier sensing multi-access with collision detection, we try to detect the collisions. If two stations, like in our case A and B, try to transmit at the same time, they're going to hear that other station is transmitting at the same time, they're going to stop their own transmission, they're going to back out of the transmission, and then they're going to wait for the random time. During this random time, the two of them are not going to be transmitting. This doesn't mean that our station C won't be transmitting. It can start transmitting at the same time or during the waiting period that A and B are undergoing, but this is besides the point. The really point is here that the stations, when they attempt to communicate and they detect a collision, they're going to stop transmitting, they're going to wait, and if there is a silence on our shared cable, only then they're going to start transmitting again. Which means that on our shared network segment, only one station can transmit at a single point in time. Now, this may not seem like a big deal, but it actually is a pretty big deal. Because think about it. Imagine that the total bandwidth available on our cable here is 10 megabits per second. If this is the total bandwidth available, it is total bandwidth available if only one station is transmitting. But what if we have three stations transmitting at once? Well, at that time, if all three are attempting to transmit simultaneously, our effective bandwidth is not 10 megabits per second, it's 0 bits per second, because when they start transmitting, they need to back off because they detected a collision. That means that if only one station can transmit on a time, the effective bandwidth that can be used on this shared segment depends on the number of stations and the amount of traffic they are attempting to send. So now it may become a little bit more clear why collisions are important. Now, in the traditional Ethernet network, the one that looks pretty much like this, collisions were a problem. Even though collisions themselves are not an error situation. This is something that Ethernet is designed to handle. It's designed to detect, and it has this algorithm, the backoff algorithm, that attempts to solve it. But nevertheless, we need to do something about it if we want to have an effective transmission in our network. Now, we are here really in ancient history of Ethernet. The evolution from the bus design that we have here was to move on to really a star design in our network. Let me explain that a little bit. So instead of connecting all of our devices to a shared cable, we decided that we're going to put some sort of a device. Let's call it a device. So I'm just going to call it D here. And we have our three stations, A, B, and C, connected like this to this device. Now, when station A transmits the traffic, device D is configured to replicate whatever comes in here, send it to B, and send it to C. In other words, we have created a hub and spoke design. And really, this device here was what hub was. You may be thinking, do we have any collisions here? In fact, we actually do have some collisions here. Because if we zoom in to what is happening in the hub, really what we have is a kind of a yellow cable. Here are A, B, and C, and they connect like this to our hub. So whatever arrives from A goes to C and goes to B. In other words, really, we have this in a smaller package. So hubs themselves were really just a multi-port repeaters of the traffic. They still maintain a single collision domain. In other words, anything that A sends, B and C are going to hear. We needed something else, something to break this collision domain apart, to allow multiple stations to transmit at the same time. This is where bridges came into play. Bridges are designed to break up collision domains, to allow for the increase of traffic between different stations that may be in different collision domains. Let me explain that. Imagine that we have a network that consists of our three devices, A, B, and C. Again, so we have A, we have B, and we have C. And they are connected to this hub. So here we have a star, but as we know, this really is one collision domain. So let's call it collision domain 1. So call 1. Now, let's have the exact same setup here, except that we are going to have devices D, E, and F. And let's have another hub here. These devices here also form a collision domain, but this is a different collision domain. As you can see, they are not interconnected yet. This is collision domain number 2. Now, if I put another hub here, so let's do that hypothetical scenario. If I interconnected these two networks by interconnecting this hub with this hub here, really, I wouldn't have collision domain 1 and collision domain 2. This would still be just one collision domain. So this really wouldn't do us any good. We wouldn't have any increase in available bandwidth in our entire network. But what we can do instead of using one collision domain like this, let me just clean this up a little bit. Collision 1, collision 2. If we had some sort of a device that could interconnect these two collision domains without passing the collisions across, we could have more bandwidth available overall in our network than if we had this as a single collision domain. In other words, if I had traffic that was happening here between A and C, and traffic here between D and F, these two types of traffic, these two conversations wouldn't have any influence, any effect on each other, because they would be in different collision domains. That means that A could speak at the same time when B is speaking. Overall, we have increased the available bandwidth in our network. this device here that accomplished this feature was called a bridge. Bridges are designed to break apart collision domains. But in Ethernet, we do have special kinds of traffic. We have broadcast traffic. Broadcast traffic is the traffic that is sent from one station and is actually designed to go to everyone in the network. Bridges are not designed to break apart broadcast domains. In other words, even though we have created here two collision domains, collision 1 and collision 2, this is still one big broadcast domain. So this here is broadcast domain 1, or let's just call it broadcast domain. So here we have it. This is what collision domain is and what the broadcast domain is. When one station is sending traffic, all the broadcasts are heard by everyone else. This is what bridges do. They design multiple network segments. They break apart collision domains while maintaining the same broadcast domain across. What if I wanted to have more than just two collision domains? What if I wanted to have, say, 3 or 4 collision domains? How would I go about doing that? Well, I would need to have a bridge-like device that has more than just 2 ports, more than port 1 and port 2. Really, this is what switches are. Switches are multi-port bridges. They are designed, again, to switch between multiple LAN segments, but there are some significant differences between bridges and switches. According to Cisco documentation, bridges are simple devices that implement their functionality in software. Switches, on the other hand, implement their functionality in hardware using dedicated processing units called the ASICs. Really, that may or may not be true, right? The Cisco correct answer is this is the difference. The real difference is that bridges have only 2 ports and switches can have any number of ports. You can have 4-port switches, 8-port switches, 768-port switches, 2,000-port switches, 4,000-port switches. These are really, really high-end devices. But switches, modern switches, do have some additional functions, some additional features that are not available in bridges. These are VLAN support, which is basically creating multiple virtual broadcast domains. This warrants some explanation. Let me talk about VLANs a little bit. We're going to talk about VLANs a lot more a bit later on, but I want to just kind of bring you in the concept of the VLAN right now, because in this day and age, talking about switching without VLANs makes no sense. So let's talk a little bit about the VLANs. Imagine that you had an enterprise, a company, consisting of 3 departments. Let's say that you had an engineering department, that you had a marketing department, and that we had a sales department. In engineering, we had 20 workstations. In sales, we had 9 workstations. And in marketing, we had 3 workstations. And the only thing that was available to us were 8-port switches. How many switches would we need for engineering department? Well, we would need to have 3 switches. For marketing department, we would need to have 2 switches, even though 1 switch would be used with 1 port only. And in the sales department, we would need to have 1 switch here. So in total, to make this network work, we would need to have 6 switches for the total number of 32 physical ports that were in use. Now, I don't know about you, but I think that this is a terrible, terrible waste of physical resources. What if we added, say, 3 more people or 4 more people into our engineering department? We would have to add a whole new switch. What if we removed 1 or 2 seats in our sales department, leaving just 1 workstation there? We would still need to have a physical switch available to accommodate for this number of workstations. This is why VLANs, or the virtual LANs, were designed. They're designed to solve this particular problem. You may recall here in the previous drawing on our whiteboard that I said that even though we used bridges or switches really because they are the same thing, they divided the collision domains. They haven't created multiple broadcast domains. If you want a real separation of traffic in a different broadcast domain so that the broadcast traffic from one department is not seen in another department, if you want to create some sort of security policies between these departments, you really want to segment this network into multiple broadcast domains. The only solution for that without the VLANs is to actually use multiple physical resources, multiple physical switches. But with VLANs, what we can do is we can take one switch and divide it into multiple virtual broadcast domains. So here we would have a broadcast domain 1, a broadcast domain 2, a broadcast domain 3, a broadcast domain 4. So ultimately, what VLANs are is just a way to segment a single switch into multiple broadcast domains. This is what switches do. As I said, I will talk about VLANs a lot more later on. Moving on to other topics, I should just mention that switches do support other advanced features that I haven't mentioned yet. These features are authentication of the users connecting to them. They support special handling of different traffic types. They support multiple broadcast domains within broadcast domains using private VLANs, for example. All of those things I will talk about as we move on to other topics. So what I wanted to mention now is just a little bit more history. I'm a little bit of a history buff, and I also think it's very important to know the history, where our products come from. When we talk about switches today, we are really talking about the transparent switches, or transparent bridges if we are talking about the bridges. These are switches that are used by Ethernet networks. They're not the only switches that ever existed in the world. We had other types of switching and bridging. We had source-routed bridges that they were used by, if I'm not much mistaken, by the token ring networks that are very, very, very seldom seen today. We had translational bridging, which was used by IBM SNA networks. Even fewer of them exist today. Transparent switches are called transparent because they are really invisible to the end hosts. What I mean by this, and going back to our whiteboard here, is that when we have two stations, let's call them again A and B, and instead of them connecting to a single bus network, we make them connect to a switch in between them. When these stations A and B attempt to communicate, they don't really see this switch. It's as if this switch doesn't exist. Really, what these guys see is the equivalent of the bus network that we had, the equivalent of the thick yellow cable that Ethernet was designed to be. There is no host to switch communication. In order for A to send traffic to B, A doesn't have to speak to the switch. It just needs to send the traffic. The switch will figure out what to do with this traffic. And incidentally, this is what I want to talk about next. When switches receive traffic from a certain host, they have a couple of decisions to make. The most important one is what to actually do with this traffic. In reality, they really have just two choices. One choice is drop this traffic if there is some security feature configured to prevent this traffic from going through. Another option is to actually forward this traffic. Accept this frame and then send it. But send it where? This is where the whole concept of different traffic types comes into play. The decision that switch is going to make what to do with the frame depends on which traffic type we are actually trying to send. Unicast traffic is the traffic from one host sent to another host. Unicast traffic is determined by the destination MAC address of this traffic, by the destination layer 2 address. The destination MAC address is a 48-bit address that is sometimes called the hardware address, sometimes it's called the MAC address, sometimes it's called the layer 2 address, sometimes it's called the Ethernet address. It's a 48-bit entity that host A here needs to know about host B if he wants to send unicast traffic to it. When switches receive unicast traffic, what they do is they first determine, is the destination MAC address something they know about? Have they actually learned this MAC address before? If they haven't learned it, they are again faced with two choices, with two theoretical choices. There is really no choice, but I'm just trying to make it easy for you to understand. If they receive traffic destined for a MAC address that they don't know about, this is something that we call unknown unicast traffic. Unknown unicast traffic is flooded by the switches. In other words, when a switch receives an unknown unicast packet, what it does with it, or unknown unicast frame, what it does with it is going to receive this frame and then send it out on all the ports except the port they received it on, as long as those other ports are in the same VLAN as the receiving port. This is what we call an unknown unicast traffic. Now, the moment switch receives any kind of unicast traffic, it is going to learn the source MAC address from this packet and put it in one of its tables, and I'll talk about the tables later on, to use for further forwarding of traffic. Now, if you're dealing with unknown unicast traffic, instead of flooding the traffic out to every single port, except the port it was received on, the switch is going to forward this traffic only to the port where this MAC address is known. Let me try to explain that on the whiteboard. So let's say that we have a switch here. And we have three stations connected to it, A, B, and C. So this is port number 1, this is port number 2, and this is port number 3. Let's say that station A wants to communicate with station B, and for whatever reason, it knows the MAC address of B. It sends out the frame that in its destination MAC address has address B. In the source MAC address, it has its own MAC address. What happens on the switch is that this source MAC address is immediately learned. We know that MAC address A is available on port number 1, but we have no idea where this B is. So what we are going to do with this traffic is we are going to accept the copy of this frame, we are going to send it towards C, and we are going to send it towards B. B is going to accept this traffic. Now let's say that B has something to say in return for this traffic. So B now sends the frame here. This here has a destination MAC address of A, and it has a source MAC address of B. Now, switch has learned where A is here. So this traffic going from B to A is not going to be flooded to C, it's just going to go from B, from port 2, and switched back on port number 1. So now, all subsequent traffic that A actually sends is not going to be flooded to C. It was just a couple of frames before B started transmitting. The moment B starts transmitting, switch actually learns the MAC address of B, so it can actually store this information and use it for further forwarding. Now, when we talk about switches, and in light of the thing that I talked about, the collision domains and the broadcast domains, if all this was in a single VLAN, this would be a single broadcast domain. So you see why it's important. It's not only about the broadcast traffic, it's also about the unknown unicast traffic, because unknown unicast traffic from A was sent to C, even though C had no use for it. This was traffic destined for B. It wasn't destined for C. But also, important thing to recognize here is the extent of our collision domain. This here is the collision domain 1. This here is the collision domain 2. And this here is our collision domain 3. Which means that in our network here, we could have a conversation between A and B, and conversation between C and, let's say, a fourth station here that we haven't used before, D, which would again be in its own collision domain. So this would be collision domain 4. We could have a conversation between A and B, and we could have a conversation between C and D without them impacting each other from the perspective of the available bandwidth in our network. Still, the unknown unicast traffic would be flooded and broadcast traffic would be heard across this network. Broadcast traffic is really not from one to one, it's from one to all. Broadcast traffic is, in our previous example, if station A wanted to send the traffic that goes to B, C, and D. It's very important to make a distinction between the broadcast traffic and unknown unicast flooding. Unknown unicast flooding is operation on the switch that switch performs in order to simulate the thick yellow cable. The broadcast traffic is a functionality of Ethernet that allows the stations to communicate one to all. It's actually fundamental for operation of Ethernet because many protocols actually rely on this functionality. For example, ARP, that is a protocol that is used to resolve the mapping between layer 3 addresses, the IP addresses, and Ethernet addresses. How did A know what the address of B is? Really, it uses ARP for that purpose. I'll talk about it later. So broadcast is really a functionality of Ethernet network that makes communication much simpler because it allows stations to dynamically learn information about other hosts on the network. The third type of traffic type that we have on Ethernet is multicast, which is really from one sender to a group of receivers. On layer 2, the default behavior of the switches is to treat the multicast traffic the same way they would treat broadcast. That means if the frame is received, it would be sent out on all ports. It would be flooded everywhere. There are advanced features on Cisco Catalyst switches that allow to limit this functionality and not send it out on all ports. This is where IGMP snooping, for example, comes into play, but this is a little bit advanced at this moment. We're going to talk about it when we talk about the multicast. It's actually a very, very interesting feature that limits the scope where the traffic is being sent. It's also important to distinguish between layer 2 multicast traffic and layer 3 multicast traffic, because not all layer 2 multicast traffic is the same as IP multicast. There are protocols, routing protocols like, for example, ISIS that don't utilize IP, but they still heavily rely on layer 2 multicasts. Also, spanning tree protocol that is used to prevent loops in layer 2 networks uses multicast frames, but it doesn't really use IP in any way. CDP as well is sent to a multicast destination, which is a protocol that Cisco uses to discover the stations connected to the ports on the switch or on the router. So multicast traffic is very, very important from the functionality perspective, and it's a third kind of traffic. It is also treated specially on the switches. So, to recap a little bit, unknown unicast traffic, it's flooded and the source MAC address is learned. It's learned and stored in a special switching table, coming up in a moment. What we mean by flooded is, as I described, the traffic is forwarded on all the ports in the same VLAN except the port it was received on. This is what I want you to remember. This is a key point, what flooding actually means in layer 2 context. Then we have a known unicast traffic. Known unicast traffic is the traffic that is sent towards the destination, towards the MAC address that switch has already learned about. And we covered how the learning is performed. Then we have broadcast traffic. It is flooded. It is sent out on all the ports except the port it was received on. I talked quite a bit about how switches learn information. Now let's see how switches store this information, where they store this information. I'm going to talk about different switching tables. The first one is a relatively simple table that we call the CAM table, or the Content Addressable Memory table, otherwise known as the MAC address table. This is a relatively simple table that stores the information about all the MAC addresses learned, on which VLAN they have been learned, and on which port they have been learned. When we perform a lookup in this table, we are really looking just for the information. Does this MAC address exist on this port, or does this MAC address exist on the table, and where is it? This is what we call a binary table. The values can match or they don't match. There is nothing in between. This table, the CAM table, is used to store the information about the learn MAC addresses. But there is another table that is used in the switches, and really the CAM table is a subset of this table on Cisco switches, and it's something that we call the ternary content addressable memory, always referred to as the TCAM table. TCAM table can be looked up not only if the values match or don't match, but we can say, okay, does this information match, yes or no, or does some part of this information match? The other bits of that information I don't really care about. So we have three possible options: match, don't match, or don't care. They're usually represented by 1 for match, 0 for not match, and X about I don't care about it. The information in the TCAM table is organized by what Cisco calls masks. This is a series of information consisting of 8 values. These values are the source IP address, the source port of the traffic, the source port logical operational unit, which is really if you are using the range of ports. For example, you had an access list that said permit traffic going to the ports between 1024 and 16,384. This would be a logical operation unit, the range of ports that we actually want to match. We have destination IP address, destination port, and destination port logical operational unit. I forgot to mention here, I see it now, that we also have the IP TOS, or the type of service information. So these 8 values, or 134 bits in total, form an entry, form a mask in our TCAM table that we can use to match against. The TCAM in Catalyst switches is used for all the access lists and used for security purposes, and all access is used for QoS purposes. That means for classification and marking of our traffic. It's important to understand that the TCAM is not an unlimited resource. You can only have so much information stored in the TCAM and also in the CAM. This is what you really need to know about it at this moment. How can you actually observe the information that is in all these tables? How can you configure these tables? How can you monitor the performance of this table is something that you should really be very fluent about. First of all, the resources on the Catalyst switch can be reallocated depending on the needs that you have. Let me talk about it in my terminal. So here I have a switch, my Cat1. First thing that I'm going to show you is something that is called the Switch Database Management, or Switch Database Manager, or the SDM template. This is the default configuration on Catalyst 3560. So here we can see that I'm using something that is called the desktop default template. Using this template, or how the resources have been allocated inside the TCAM, allows me to store information about 6,000 MAC addresses, that I can have 1,000 IGP groups and multicast routes, that I can have 8,000 IPv4 unicast routes, and so on and so on. You can see that the resources have been allocated in a certain way. You can change the allocation of the TCAM resources using SDM prefer command. And here you have different templates that you can use for that purpose. I doubt that you will need this in many cases. One particular exception is if you want to configure IPv6 routing on your switches. If you want to do that, you absolutely must change from the default SDM template. You need to change it to something that is called the dual IPv4 and IPv6 template, because otherwise IPv6 routing is not supported on 3560 and 3750 switches. So going back to our topics here, the TCAM is really, other than the SDM template, it's self-sufficient. You don't need to configure it in any way. You just configure the access list, and the access list will automatically map to the TCAM masks. But you can see how many resources you are using out of available resources. You can do that with show platform TCAM command. Let me show you that. So with show platform TCAM here, I can see what is the actual utilization of my resources. And as you can see, unless you are really doing something unusual, unless you have large number of routes, large number of access lists, and by large, I really mean large number of access lists, you are probably going to be fine with the default available values in your Catalyst switch. Other table that you need to be fully aware of is, of course, how do you monitor information in the CAM table, in the MAC address table. MAC address table can both be configured and monitored. By configuring CAM table, MAC address table, we mean, can you configure static entries there? By default, I told you that the MAC address table will be automatically populated when the information is learned from our traffic. But you can also statically map certain MAC addresses to certain ports and VLANs on our switch. Let me show you that in action. So here I have show MAC address table. This shows me all of my MAC addresses that have been learned on this switch. So here I can see the VLAN, the MAC address, what kind of type it is it dynamic or is it statically learned, and on which ports is this learned. CPU here refers to the switch MAC addresses. So anytime you see a CPU here, you know this is the local switch. This is the MAC address on this switch actually. And here I can see that in our VLAN 1, I have some number of dynamically learned MAC addresses on different ports. But I can also tell my switch that, for example, I have MAC address static, and let's map some fictitious MAC address here to VLAN 1 to port number 1. Sorry. So now, if I take a look at my MAC address table for VLAN 1, and as you can see, you have different options. You don't always have to look at the whole table. So here I'm using show MAC address table dynamic VLAN 1, which will show me the MAC addresses in VLAN 1 that have been dynamically learned. I'm not going to see the MAC address that I configured because it's not a dynamic one. But if I say static and then interface fast Ethernet 01, I'm going to see here that I actually have a statically configured MAC address on fast Ethernet 01 here. And if I do just show MAC address table, I can see that I have all sorts of different information. For example, I can see how many dynamic addresses I have. If I do show MAC address table count, I can see the information about the address allocation, really. How many dynamically learned ones, how many statically configured ones I have. And please note that here it says static address count 1. If I do show MAC address table, that doesn't really add up. It doesn't add up because all of these CPU ones, they are not really taken into account. The The only thing that we are taking into account is the actual static address that is mapped to a port. Now, we can map the static address to a port either using the global configuration like I used it here, or we can use per port settings, but that's part of the port security configuration if you want to restrict the learning capabilities of the port for protection purposes. So you can monitor the information about the CAM table using show MAC address table. And this is really what you need to know about the switching basics and about the different switching tables.